This is our last set of notes for our friendly introduction to multivariable calculus, which is exciting because everything in multivariable calculus basically leads up to these three main theorems that give us a way to convert something like a single integral to a double integral, or a double to a triple, or vice versa. But these are the three main results that we've sort of been working toward this entire time. Like, we've learned all about these multiple integrals, and now we'll actually put them to use. So the idea behind all of these three sections that we're going to talk about today is that sometimes these integrals, even single integrals, but definitely double integrals, which we will get to, certain integrals can be really, really complex to compute. So we have three results that it's sort of actually a little counterintuitive, but we have these three main results that will basically give us a way to take a single integral and convert it to a double integral of this new expression, which a lot of times, even though we're dealing with a double integral over here, can make our lives a lot simpler and can make our computations a lot easier for us. And then, of course, with all of these results, you can go the other way too. So if someone gives you a double integral, you can use this to go back to a single integral. But this first one is called Green's theorem, and Green's theorem basically says if you have some region in the plane, let's see, let me move my. So you have some region in the plane which is enclosed by what's called a simple closed piecewise smooth curve. So basically what that means is you have some curve, and closed means that it meets up, so it's actually basically equivalent to a circle. Oriented counterclockwise, so we do have this orientation here, and we're going to call this curve C. Now there's some, I guess, restrictions on this. It says simple, which means simple just means it doesn't like loop back on itself. Like, this would be a problem. That's not a simple closed or a simple curve. This is a simple curve. Closed means that it closes, so like that is not closed. It has to loop all the way back on itself. And then piecewise smooth, that just means no corners. Oriented counterclockwise. So basically we have a friendly curve, and this friendly curve encloses this region in the plane. All of this is going to just be dealing with two dimensions, and then ultimately when we get to Stokes' theorem later, we'll make this entire situation more curvy, and this region won't be flat anymore. But for now, we'll start with this nice plane region. So around this curve, we can take a line integral. So we can integrate around this curve C of something that looks like this. We have two different functions. We're integrating one with respect to x. We're integrating a second one with respect to y. Green's theorem says instead of integrating around that curve, doing this line integral around this curve, instead you can take a double integral over this region of basically this difference of their partial derivatives. So this might seem counterintuitive to take this line integral, so single integral, and turn it into a double integral, but let's see this in action. We'll do three examples of Green's theorem. So the first one is use Green's theorem to evaluate this line integral, x squared y with respect to x plus x with respect to y. Along the triangular path, I'm going to draw the path first, and I'm going to scale this up a ton, otherwise our triangle is just going to be right here. So I'm going to say our triangle starts at 0, 0, and I'm going to say 4 of these little spots are actually 1. So here's 2. And then here's 1, and here's 2, just so we can actually get an idea of the path. So this triangular path connects 0, 0 to the point 1, 0. So here's part of our path, and it's oriented this way. It connects 0, 0 to 1, 0. And then it connects 1, 0 up to 1, 2. So 1, 0 connects up to 1, 2. So here's our orientation. And you'll notice, first of all, this is a simple closed curve. It is piecewise smooth, so there are corners, but I have these pieces where there are not corners. So that's the piecewise smooth part. This is fine. Let's see, it's simple, it doesn't loop back on itself, there's nothing that looks like that. This entire thing meets our criteria for Green's theorem. So Green's theorem says instead of integrating in these three different sections, which would be sort of tedious to integrate along this path, then this path, then this path, Green's theorem says instead, let's just integrate over this region. So when I use Green's theorem, I'm going to take this original integral and say that it is instead equal to the integral over the region, here's our region in here, of our second function, our second portion of this function. I'm going to call it g, even though I haven't written that yet. The partial of that with respect to x minus the partial of the first function with respect to y. Now, when I'm saying this, I'm using this guy as my function f, and then this is my function g. So this is equivalent to integrating over this region. Let's see, so the partial of g with respect to x is 1, and the partial of f, this first little function with respect to y, is x squared. So here's my new double integral, and now I just have to set up limits and actually integrate this thing. Also, you'll notice by taking those partials, I made this integrand a little bit simpler, so that's nice. So this is one of those double integrals that falls into the situation that it looks to me like the x limits are very simple to see. X is integrated from 0 to 1. And then y is the one that sort of has these weird function limits. So I'm going to integrate with respect to y first, because 0 to 1 with respect to x is going to be the simpler way to do this. So I'm going to set this up integrating with respect to y first. And y goes from 0, and then I just need to write what this function is all in terms of x. So I have this y equals, well, this is just a line, like this segment that connects 0, 0 to 2, 1, or sorry, 1, 2, is just the line y equals 2x. So there's my limit here. My integrand is 1 minus x squared, and my first integration will be with respect to y. So 0 to 2x, and then 0 to 1. So simple double integral. Actually, really simple computation now that we've converted it to a double integral. So my first integration from 0 to 2x is with respect to y. So that first 1 is going to integrate to y, and then x squared integrates to y, x squared, and I'm evaluating this from 0 to 2x. And then when I'm done with that, I'll integrate again with respect to x. So 0 to 1. From 0 to 2x, well, 0 kills the entire thing off, so really this just means plug in 2x for everything. And when I plug in 2x for y, this just becomes 2x. And when I plug in a 2x here, I've got 2x times x squared, so really this becomes minus 2x cubed. And I'm integrating with respect to x, and you can see how simple this is getting really quickly. So then I'm going to integrate, actually I don't even need another integral. I'm going to integrate from 0 to 1. 2x integrates to x squared, and 2x cubed integrates to x to the 4th over 2. And I'm going to plug in 0 and 1. 0 kills the whole thing off, so really this just becomes plugging in 1, which is 1 minus 1/2, or 1/2 is the final answer. Now if I had actually done this as a line integral without using Green's theorem, I would have had to set up this integral, this second integral, and this third integral, and instead we converted it into a double integral, made the integrand simpler, and then it was a really simple computation to get to the answer. So that's one example of how Green's theorem can make our lives a little bit easier. So here's our second example. Use Green's theorem to evaluate. Now this integrand is a little bit more complicated, but again, I have some function, which I'll call f, that I am integrating with respect to x, and I have the second function g that I'm integrating with respect to y. And I'm going to integrate this around a circular path. Not a very good circle, but that's okay. Oriented counterclockwise. x squared plus y squared equals 1, so let's imagine that that's a perfect circle of radius 1 centered at the origin. So Green's theorem, again, says instead of integrating around this circular path, let's integrate over this region that it encloses. This is our region, I'm going to call it R. So Green's theorem says instead of integrating over that path, let's integrate over this region, and I'm going to integrate the partial of the second function, this g function with respect to x, minus the partial of the first function with respect to y. And I just have to set up this integral, and hopefully this is easier than what I started with. So, integral of this over this region. Now, partial of g with respect to x, well, when I differentiate this little function with respect to x, cosine of y goes away. It's just a constant. So this is 3x squared, and then minus the partial of the first function with respect to y. So again, e to the x goes away when we're differentiating with respect to y, and this becomes minus 3y squared. There's my area element. Now, double integrals are still friendly, so I'm going to pull the 3 out to the front and say this is the same as integrating x squared minus y squared with some area element. Now, let's just stop for a second and notice that I do have clear limits for both x and y, but basically curvature is happening everywhere. Like I don't have one straight, I guess I don't have one variable that has just straight, like linear boundaries. So because of that, I'm going to convert this entire integral into polar coordinates. So when I convert this into polar coordinates, remember, I get something that looks like, for some reason now I'm doubting what I did there. This is supposed to be, oh yeah, I totally made a typo. When I differentiate this with respect to y, it's really minus negative 3y squared, which is why I was puzzling over the polar coordinates, because in my notes, this comes out to be really simple. X squared plus y squared, which when I convert to polar coordinates just becomes r squared. So that makes our integrand a lot easier. So I really have r squared. And now I'm going to set up my polar coordinates, but before I do that, let me just talk really quickly about converting the area element into polar coordinates. So when we're dealing with polar coordinates, remember our little slices of the function are like these little pie slices like this. So our area element is really something that looks like this. There's our tiny area element, really, really, really small. And I kind of like briefly went over this on one of the other examples, but I just sort of stated it. I didn't really explain why we convert in the way that we do. So this is dA. This little tiny angle is d theta. And then we just need to figure out how this converts to r and theta. So this little change in the radius is called dr. And then I guess that only leaves the question, like, what is this? Because it's not d theta, it's actually a length. So you have to sort of go back to what you learned in like algebra 2, and remember that when you're in radians, we have this nice formula for arc length, which is the arc length is r theta, which makes this tiny, tiny little arc length r d theta, because our angle is tiny, so r d theta, and then this is a tiny change in the radius. So this little area element, dA, is basically surrounded by this little dr on one side and this r d theta on the other. And the idea is this is so close to the shape of a rectangle, where one side is r d theta and the other side is dr, that we basically say it's close enough that we're going to call the area element, the area of the entire thing, just the length times the width here. So when you're in polar coordinates, the dA becomes r dr d theta. So I think that's a little bit confusing because sometimes we just want to say that dA is the same as dr d theta because we're pretty used to saying the dA is the same as dx dy. But when we're in polar, this little length along the bottom of this basically rectangle is actually r d theta. It's not just d theta. So dA converts to r dr d theta when we're in polar coordinates. And that's really important to know because if you forget that extra r, it kind of messes up your integral. So this dA over here is going to turn into r dr d theta. And now I just have to set up my limits. And this is a circle, so my limits in polar coordinates are actually really easy. My limits with respect to r, well, this circle is a radius 1 circle, so it's going to go from 0 to 1. And theta is going to go from 0 to 2 pi. So I just need to evaluate this integral that actually became really, really simple when I converted it. So this becomes 3 times the integral from 0 to 2 pi, and then this is just r cubed. So when I integrate with respect to r, it becomes r to the 4th over 4, and I evaluate from 0 to 1. This is all with respect to r, and then I'll use my second integral to integrate with respect to theta. So 3 times the integral from 0 to 2 pi of 1, I don't know why there's a dot there, 1/4 d theta, which becomes 3/4 times the integral from 0 to 2 pi of just d theta. And our final answer then is 3/4 times theta, where theta goes from 0 to 2 pi, and that makes our entire final answer 3 pi over 2. For this integral that actually could have been sort of difficult if we first of all integrated this complicated function over a circular path. Using a line integral to do that computation would have probably been a lot more complicated, and once we converted it into a double integral, it became first of all a really simple double integral, and we converted that into polar coordinates and it became a very simple calculation. So that's another way that Green's theorem works for us. So this last one is a little bit different just because it doesn't give us an exact curve for C. So this one says use Green's theorem to evaluate this thing that looks a little bit complicated, but actually before we even start, I'm going to rewrite it because you can see that the dx and the dy differentials are written right in there in the numerator. So I'm going to just convert those a little bit. Negative y over x squared plus y squared, all with respect to dx. And then I'm just separating this into two fractions. Oops, x squared plus y squared, all with respect to dy. The weird thing about this one is it doesn't give us an exact curve. It just says C is a closed curve oriented counterclockwise. So, okay, this reads just like Green's theorem so far. Some curve oriented counterclockwise, right? But C does not enclose the origin. So I have to not enclose the origin here. So maybe here's C. Oriented counterclockwise, C does not enclose the origin. I'll talk in just a second about why that's important, but let's just use Green's theorem here. So again, Green's theorem says forget about the line integral. Let's just integrate over this region. Convert this to a double integral over this region with the partials, first of the second function with respect to x, and then the first function, this guy over here, with respect to y. And we'll set up this integral. Hopefully it's easier to compute, and we'll use that instead. So let's compute the partials. The partial of this first fraction that I've lost now is the partial with respect to x of x over x squared plus y squared. So just going back to like simple calculus and quotient rule, I'm going to say ho times d high. Well, d high with respect to x is 1. minus high, and then d ho. Well, d ho with respect to x is just 2x, all over ho ho, which simplifies, when I simplify this entire thing out, I get x squared plus y squared minus 2x squared all over the denominator squared, which then simplifies to y squared, and then the x squared and the negative 2x squared combine to that. X squared plus y squared squared. Okay, so now let's do the same thing, but differentiate with respect to y of the first function, which I think was, yeah, negative y over x squared plus y squared. So again, just quotient rule. So ho d high minus high d ho, which is 2y now, all over ho ho. And when I simplify that, this becomes negative x squared minus y squared, and then I've got minus a negative, so really plus 2y squared all over x squared plus y squared, the denominator squared. And when I simplify that, let's see, I've got this negative y squared, and then I've got, oh, I'm sorry, I've got positive y squared. Yeah, positive y squared, because negative y squared plus 2y squared. And then I've got the negative x squared all over x squared plus y squared squared. Okay, now one of the things that we didn't talk about so much in the statement of Green's theorem on the previous page or 2 pages ago is that f and g have continuous partial derivatives on that region. So the partial derivatives have to be continuous, and also just the original functions have to be continuous on our region, which just taking a break from what we're doing really quick, that's why this can't enclose the origin, because both of these partials have x squared plus y squared on the bottom, and if we included the point 0, 0, that would break the continuity of these partials. So that's why it's important in the problem that it says any curve that doesn't enclose the origin. It's like, if it did, well then it sort of breaks the entire Green's theorem situation, we can't use it anymore. But as it is, okay, so there's no problems with continuity here. We know that the partials with respect to y and with respect to x are, let's see, actually they're the same, right? So y squared minus x squared over the denominator squared, which is kind of interesting because that makes Green's theorem pretty easy to use here. Green's theorem says just integrate over the region of partial g with respect to x minus partial of f with respect to x, or with respect to y. Is that right? Yeah. But these are the same. Like partial g with respect to x and partial f with respect to y are the same. So this entire thing becomes 0, and it's a double integral over, I don't even know the region, because I didn't have to know the region, of 0, which makes our entire answer 0 without doing any computation at all. So that's our section on Green's theorem. Green's theorem gives us a way to take a line integral and convert it to a double integral, which, even though it's a little counterintuitive, it actually can make our lives a lot simpler. Now, just to sort of foreshadow what we're about to do, Stokes' theorem later says instead of imagining that this curve, this closed curve, encloses this flat region R, what if our curve encloses something that is actually like a curved surface? So Stokes' theorem basically takes this one step further. It takes Green's theorem one step further and says, what if this region isn't flat anymore? And then how does this work? So we'll get to that in just a few minutes, but right now you are ready for exercises 1 through 4, which are all about Green's theorem, pretty simple examples of Green's theorem. or you can go on to the next video, which is about the divergence theorem.